Welcome everyone to the session on practical quantum algorithms. I'm Joana Fraxanet. I'm part of the quantum algorithm engineering team, and today I'm going to be talking about a specific type of quantum algorithms, which are variational quantum algorithms. I'm going to start with the motivation and why these algorithms have been very important. Then we're going to see how to build the structure of a general variational quantum algorithm. And then I'm going to show some examples like the VQE or the QAOA and other examples on QML. Finally, I'm going to review the challenges and limitations of these algorithms nowadays, and I'm going to end up with a conclusion. I'll start with the motivation for variational quantum algorithms. As we all know, right now we have to think about algorithms that can be implemented in near-term quantum hardware, and this means that we have a set of limitations to take into account. To start with, we have access to devices that have a limited number of qubits. For IBM devices, all the number of qubits are now above 100, but still this is not so much if we want to implement, for example, algorithms as Shor in its full glory. On the other hand, and maybe more problematic, we don't have access to error correction yet. This means that we have to work with devices that have noise, and this noise is going to affect the output of our calculations. On one hand, this limits the depth of the algorithms that we can run, meaning that we cannot have so many gates, because otherwise at some point the algorithm would just be outputting random quantum noise. And on top of all this, we have limited qubit connectivities, so we have to adapt to the topology of the specific device we're using. For IBM devices, we have that the topology is a heavy hex, and then we have to think about mappings that can that can respect this topology. So because of all of this, we require algorithms that are noise resilient, meaning that they can accept some level of noise, that are shallow, that they don't have so many gates, and that are adaptable. A good idea to try to find algorithms that respect all of these things is the hybrid approach. So this would mean using the quantum device or the QPU for example, state preparation, entanglement, creating entanglement, or then doing the measurements. This is what the QPU is good at. And then using a classical device for other things. Other things could be parameter optimization, so trying to update the parameters or the characteristics of the quantum circuit we're running, or post-processing. We can have several types of post-processing, and some of them can be more involved than others. We're going to see that at the end of the presentation. So this hybrid approach can include many types of algorithms, and in particular, variational quantum algorithms are included in here. For variational quantum algorithms, we really use the classical computer for parameter optimization. So even though variational algorithms have been promising, they have been key in leveraging quantum computers, the ones that we've had available until now. They do present challenges for scalability and reliability, both in near-term and fault-tolerant settings. So we're going to see all these challenges throughout this presentation, and also we're going to see how in some cases they still apply and they can be interesting for leveraging quantum computing. As I said, they can be applied to many different cases. Here's a bit of a motivation for variational quantum algorithms, seeing the different fields in which they apply. In this presentation in particular, we're going to see specifically a use case which would be finding ground states. Finding ground state, for example, for quantum chemistry Hamiltonians, or for condensed matter Hamiltonians, or for other systems that, for example, can describe high energy physics. And the star algorithm here would be variational quantum eigensolver, so the VQE. I would say that maybe it's one of the most known variational algorithms. On the other hand, we can also use variational algorithms to solve combinatorial optimization problems. We're going to see that an example for this type of problems is QAOA. And then we're going to briefly mention some examples of quantum machine learning. Quantum machine learning is a huge field of research, but many of the algorithms that are included in there are variational. And some examples are variational quantum classifiers or generative models. As you can see here in the slide, there's other applications, but we're going to focus on these ones since I believe they are the more important ones. So going back to what are variational quantum algorithms, let's now see this in more detail. And the idea here is that I'm going to build the different stages that are needed to build some general variational quantum algorithm. And then we're going to see how this applies to VQE or QAOA or other examples. So First of all, we need, as I said, to execute a quantum circuit and a set of measurements. This happens at the QPU, the quantum processing unit. And the output of this execution and the measurements is going to go into a classical computer where we're going to evaluate something called a cost function. And we're going to use this to optimize the parameters of the quantum circuit. So then there's a closing of the loop, and the idea is that we iterate over this loop until we converge to the solution that we're looking for. So if we look more closely into what happens in the QPU, we see that we have on one hand the parameterized quantum circuit, and on the other hand the measurement. This parameterized quantum circuit is just a set of gates, a quantum circuit that depend on a set of classical parameters. These classical parameters are usually angles of certain rotations, but it's just a vector of parameters. So this is what we call the ansatz. The ansatz define how we place all these gates in the quantum circuit and what kind of gates we have. And depending on this, we're going to be able to create some set of states or another. For example, this ansatz here has some rotations on the y-axis, and then it has some c-nodes. The c-nodes, for example, here are put in a linear fashion. This is a real amplitude ansatz. It has 2 repetitions, as you can see here, and it's applied to 4 qubits. This is a very general ansatz that can be used for problems in which we don't have much information on the problem. But then there's other ansatzes that can be used for these cases, or if we have information, we can choose something that makes more sense. Apart from deciding which is the ansatz we want to use, and we're going to see later with the examples how this is a big decision that it's going to impact greatly on how our algorithm works, we also need to choose the initial parameters. So we're going to start somewhere, and this means that we need to start by defining all these angles in the y rotations, in this case, by inputting some number. Here it's important to take into account that the parameters sometimes they're constrained. So for example, here if we're talking about rotations, we're going to take parameters between 0 and 2 pi. As I was saying, there's many other options for ansatzing. And if one looks at the Qiskit circuit library, this is in the documentation, you can see many other examples and see the characteristics of each of them and why it could be relevant for your problem or not. So typically, the real amplitudes one is widely used. The efficient SU2 is also quite typical. And here you see others that have more to do with specific problems. For example, QAOA will be, of course, implemented for the QAOA algorithm. And then there's some of them that might have to do with quantum chemistry, for example. So now that we've defined our parameterized quantum circuit, we cannot yet run it on the actual quantum backend, so the device. First, we need to change it a bit so that it's allowed for the quantum device. And this means transpiling this parameterized quantum circuit into a QPU. So in order to transpile this parameterized quantum circuit, what we're doing here, first of all, we choose an efficient qubit mapping. So we choose each of these 4 qubits, which of the qubits of the actual device is going to be. If the connectivity does not match, we'll need to insert some swap gates, because at the end, every time we have a 2-qubit gate, we're connecting 2 qubits and they need to be connected in the device. And then we're going to translate the gates of our ansatz to the backend native gates, because a given backend has a set of native gates that might not be the abstract gates that we define at the beginning. Having said this, the backend's native gates is always a universal set, so you can express everything, but we just need to make some changes, and sometimes this can increase the depth in our circuit. Let's say, for example, the circuit that I was showing before, the real amplitudes. Now we see that each of the 4 qubits maps to some qubit in the backend. The gates, the set of gates has also changed here, so we don't have C-nodes anymore. Now we have CZs. And we have some added rotations here. If you want to see how this is done in practice, all this transpilation has a set of steps, and it needs to be optimized at the maximum to kind of reduce the depth of the final ISA circuit, which is the transpiled circuit. You can see this in the quantum computing in practice course in the learning platform. So we add this execution of the ISA circuit as one more step, and now we have the preparation of the quantum circuit, execution of ISA circuit, and measurement. Let's now focus on the measurement part. So for variational quantum algorithms, we usually want to measure some expectation value of an observable. This is going to define later the cost function. This is not always the case. There's some cases of variational algorithms that might be a bit different, but in general, for everything we're going to see, we need an observable. This observable is usually given by the problem. So we're going to see later how this observable can be, for example, the Hamiltonian in cases in which we're computing energies. or it can be something else in other cases in which we have a general optimization problem. Then to compute this expectation value, we need to run the circuit several times. So what we do is to have a number of executions, which we call number of shots. And every time that we execute, we measure, and we're going to use all this data to reconstruct the expectation value of an observable. Let's see how, for example, this is applied when you have a very simple observable. Imagine that we have a quantum state that is the superposition of 0 and 1. And we have an observable here that it's the X Pauli matrix. So basically here we would need to prepare our quantum state with a Hadamard gate. Then we would need to rotate the basis at which we're measuring, because usually we measure with a Z basis, and here we want to measure an X observable. This is done in this case also with a Hadamard gate. And we measure a number of times. This gives us some histogram, and then we can compute the expectation value of the X observable as the mean of this histogram. And we also have a variant associated to it. If we increase the number of shots, we're going to increase the precision at which we're measuring this expectation value. So as I said, the observable is given by the problem. Now we've seen a very simple observable, but most of the times observables are not that simple. In fact, any observable can be a linear superposition of Pauli strings, which would be sets of these Pauli gates or Pauli matrices applied to different qubits. So let's imagine, for example, we have this observable in the screen. So you have the Z Pauli matrix applied to qubit 0, X applied to qubit 1, then plus Y applied to qubit 1, and X applied to qubit 2, etc. In this case, we have 5 terms, and one would think that we would need to do, so if we have a number of shots of 1,000 shots, maybe we need to do for each of these terms in the sum, 1,000 shots, measure the Pauli string, doing the associated basis rotations in each qubit, and then reconstructing the whole thing. This should in principle be the case, but there's ways of reducing the number of circuit executions. Otherwise, this would increase like crazy for some kind of observables. So one of these things is grouping. Actually, we can group these terms by commuting terms, and these can be reconstructed at the same time. So we don't need to repeat the number of shots. Then there's other things that can be done. If the coefficients, in this case, all the coefficients are 1, because we just have a sum of terms with no different amplitudes. If they would be different, maybe we could try to regroup then the shots in ways that for the most important ones, there's more shots. So going back to the summary, we have that we have to define a parameterized quantum circuit. Here is choosing an ansatz, choosing a set of initial parameters. This is going to be very relevant to converge to the right state. Then we need to transpile to the QPU. Then we need to choose an observable. This comes with a problem. The number of shots or the precision that we want to have, and a measurement strategy. The measurement strategy can be, for example, grouping in cases in which the observable is very complicated. Okay, so now we can go into the classical computing part. And here, when we have the results from the ISA circuit, we can still do some post-processing usually. So it's good to, again, take into account that we're working with noisy devices, and therefore error mitigation can really help to recover the signal a bit and work with better expectation values. So this would happen here when we get the measurement outcomes, and we know some information about the ISA circuit, we might apply some error mitigation. You're going to see details on error mitigation in some other session, but for now, let's just mention it here because it's important. Then after this, we have the cost function evaluation and the parameter optimization steps. So cost function evaluation, this can, in some cases, just be the expectation value that we got is the cost function, and we're minimizing that. So, for example, if we want to minimize the energy because we want to find some ground state energy, as we're going to see with the VQE, then we would just consider that the cost function is the expectation value of the observable. In other cases, it's a bit more complicated. Maybe we need to reconstruct some function of it. We need to make some changes. And then once we have the cost function evaluated, what we want to do is minimize this cost function. Therefore, we need to optimize the parameters that on which this cost function depends, that is the parameters of our parameterized quantum circuit, and keep changing them until we minimize this value. For this parameter optimization step, we have many choices. So there's, classical optimization has been a field for many years. There's been a lot of developments. and one can choose between many different types of classical optimizers. Now the question is which ones make sense for these kind of algorithms in which we're sampling from a quantum processing unit. So this will depend on the problem. It's not an easy choice, but we can classify these algorithms in different ways. So, for example, we can classify this between gradient-based optimizers and gradient-free optimizers. Gradient-based optimizers would be great optimization algorithms that what they do is to compute the value of the cost function at some point and also the gradient for different directions, and then we choose the direction in which the gradient is greatest. So the steep, for example, the gradient descent is just going towards the minimum by choosing the descent of the gradient. The problem here is that we need to compute gradients, and in order to compute gradients, we need to execute circuits again. We need to extract them from the parameterized quantum circuit. There's different ways of doing this. One way is approximating the gradients with functions as the one you can see here. Another way is using the parameter shift rule that makes sense of the fact that these parameters are actually in the rotations, and we know how to make the derivatives of the rotations because these are sines and cosines. But then there's other approximations to gradients, and the gradient descent would be the simplest example, but then we have methods that have improved over it, like SPSA or ADAM, or etc. And then we have gradient-free methods. Gradient-free methods would not need to compute these gradients, but in some cases we also need to do some more executions in the quantum circuit. An example here could be genetic algorithms. So differential evolution falls in this category. And in this case, we just have a population that it's like outcomes of different parameterized quantum circuits at different points. And we kind of grow this population by varying a bit the parameters and then choose the ones that are best and keep growing and reducing the population until we end up converging to the value that we want. There's also the Cobila optimizers and many others. We can also classify these optimizers differently, for example, between local optimizers and global optimizers. Local optimizers would, for example, gradient descent is an example of this. They look at the neighboring area of the point at which we are. So this means that they might be trapped in local minima because they don't see the whole landscape. But whenever we're relying on the gradients, this is usually the case. On the other hand, global optimizers see the whole energy landscape, so they can be better at not getting trapped at local minima, even though there's some examples of local optimizers that have been improved to not rely so much on the neighboring area. But they might have other disadvantages. So there's really a world of optimizers. Actually, if you look at the Qiskit documentation, you're going to see that many of them are listed there. You can see how they work and the explanation. And then decide which one you want to use. I would say Cobila, SPSA are quite typical. Maybe genetic algorithms not so much yet, but they're starting to be used in some cases. Adam is also a good option. There's the gradient descent maybe is the typical one that it's explained, but it's the most simple one. So going back to the overview, now we have the parameterized quantum circuit. As I said, preparing the ansatz, the initial parameters, transpiling, and measuring an observable. And then we evaluate the cost function. We choose how we want to optimize over it. This might mean that we need to execute the circuit more times to obtain gradients or some other sets of parameters. And usually for the optimizer, it's not only about choosing the optimizer, but we also need to just choose a bunch of hyperparameters, like how many iterations do we want to do, which is the step that we take at each step of optimization. Like we take large steps and then we explore the landscape faster, but maybe we miss things or not. When do we assume that we've reached convergence? So all these are questions to answer. This is what makes variational quantum algorithms complicated in a way. There's a lot of heuristics on them, but also adaptable and flexible. We can adapt a bit to the resources that we have. So with this, we've finished the review on how to build a variational quantum algorithm, and now I'm going to go through some examples of them and show you how each step relates to some specific things that need to be implemented. In particular, we're going to see the variational quantum eigensolver, the quantum approximate optimization algorithm, and some QML examples, variational quantum classifiers, and generative models. The variational quantum eigensolver, this is the one I'm going to start with, was developed in April of 2013, so it's been some time already. Since then, there's been many generalizations of it. It has been applied to many different problems. We're going to see some of them in which maybe it has some challenges, and some cases in which it was more successful. So, well, VQE, as I said, has been applied for many different use cases, and it's used to estimate an upper bound of the ground state energy of some system. So the idea is to obtain the ground state energy, but if we don't converge, we know we're always going to be in an upper bound of it. It can be different types of systems. So, for example, it can be used, and it has been used, to study high energy physics systems, to understand, for example, the states with quarks and so on, like fundamental nature of particles and forces. It has been used to study materials, to study how these different ground states in materials, what are their characteristics. And I would say that the most important application of VQE has been quantum chemistry. So to understand how some molecules work, by knowing the ground state energy of some molecules at different configurations, we can understand, for example, some reaction rate of these molecules. We can understand which is their stable configuration, and this can be very useful, for example, for drug discovery. So focusing a bit on this, but we're going to see other examples too. Let's see how the variational quantum algorithm, variational quantum eigensolver works. So it's based on the variational principle, and this is the reason why we obtain an upper bound of the ground state energy. And the thing is that if we take an arbitrary state, and it has an associated energy, because we just take this state and we do the expectation value with a Hamiltonian, we get an energy. Turns out that this energy is always going to be larger or equal to the ground state energy. Therefore, we can take different states. These would be, for example, states that can be expressed by our ansatz with our parameterized quantum circuit, and evaluate them. And we always have an energy that it's larger or equal to the ground state energy. If we minimize over this set of states, we would in principle convert to the ground state energy, which is what we want. One could think that we could try the different states and then see, which one has the lowest energy. This is not a possibility because we have many states in the Hilbert space. So we need to find clever ways of optimizing. And that's why we have this whole variational quantum eigensolver, and why we need optimizers to move through a good path, let's say, that doesn't take too long in energy landscape to find a ground state. Let's see how VQE applies to a quantum chemistry problem. So let's take, for example, this molecule you can see in the screen. This is a large molecule. A molecule is defined by the configuration of atoms and also with the basis set that we're choosing. So, for example, this molecule, we choose this basis set you can see in the screen, which is a basis of orbitals for each atom. Then usually what one does, it solves the Hartree-Fock, like the Hartree-Fock problem. Then you get the molecular orbitals. This is the basis of orbitals in which we can express the second quantized Hamiltonian, which would look like this. So here we have a Hamiltonian, we have some coefficients that we can compute for this molecule, and this is a fermionic Hamiltonian. Then we could map this to qubits using the Jordan-Wigner transformation, for example, and we would end up with a Hamiltonian that is expressed for qubits. In this case, we end up with a Hamiltonian on 72 qubits, which is quite a lot. Now, knowing that our goal is to minimize the energy, so the expectation value of this Hamiltonian, we need to think about parameterized quantum circuits of ansatz that will be able to express the right set of states that could potentially minimize this energy. So we want an ansatz that expresses the subspace of Hilbert space in which we can find our ground state, and this is very important. But at the same time, we want an ansatz that can be implemented in the hardware. So we don't want an ansatz that is extremely complicated because it might have a very large depth, very large number of 2-qubit gates. And this is problematic because, again, we're working with noisy devices. So an option is to choose a hardware efficient ansatz. This would be kind of forgetting about the problem and saying, okay, no, we want something that maps well to the hardware, and we just hope that this expresses the right set of states. And this is done in some cases. If you create enough entanglement, you should be able to reach different areas of Hilbert space. And for example, the real amplitude ansatz that we saw before, this would be a hardware efficient ansatz. On the other hand, we can do the opposite. We can do, okay, let's forget about the hardware. let's think about our problem, and let's try to find an answer that is physically motivated. An example of this would be the unitary coupled cluster singles and doubles. What we do here is say, okay, you know that the ground state of this molecule is going to be a superposition of slated determinants of different configurations of electrons. And the configurations that are going to have the most contribution to this ground state are probably going to be the ground state, and then some excitations of the ground state corresponds to the Hartree-Fock state, means all electrons in lower energy configurations, and then some single electron and double electron excitations on top of this. Other types of excitations might not be so important. So we consider these excitations, we encode them in an ansatz, and then the amplitudes of these processes are going to be the variational parameters. This can be very good because we're really like targeting the problem, but what happens here is you end up with an answer that it's all-to-all connected. So when you try to do the ISA circuit, you end up with huge circuits. And then you can try to do something in between. This was proposed not so long ago, 2023. This example of something in between is the local unitary coupled Jastrow ansatz. And it takes some ideas from the coupled cluster, in fact, a bit different because this is the Jastrow formalism, but it's also these ideas of single and double electron excitations. And at the same time, it approximates a bit to be local, so to take the connections that we already have in our hardware. So this would be a good candidate. And then on top of this, it's important to start with a good set of initial parameters, as we mentioned before. In particular, for quantum chemistry, if we're using this type of ansatz, we start with a Hartree-Fock product state, which, as I said, is just having the electrons in the lowest energy configurations. And then we're just flipping some of the qubits. And then the parameters of the ansatz can either be initialized randomly. This is going to probably make our life more difficult, or they can be initialized using some previous classical calculation so that we already start at a good point. If we choose this local unitary coupled Jastrow ansatz, we will need to map it into the hardware, and we need to do this mapping in a clever way. So this ansatz is built in a way that the mapping already comes with it, let's say. So for example, for the N2 molecule, this is a bit of a smaller one, this is 58 qubits, we will see this mapping of the ansatz, and this would be the corresponding gates. So with this, we have the ISA circuit, and now we have to perform a set of measurements. So far, so good. Things look promising. But let's see what happens when we try to do measurements with this Hamiltonian that we have in the screen, the qubit version of it. This is definitely a complex observable, so we're going to need to perform many measurements, and we're going to need to implement measurement strategies like grouping and so on. But even with this, the problem becomes very complicated. Just to give you some numbers, this molecule on 72 qubits, if you look at this Hamiltonian for qubits in terms of like a linear combination of Pauli strings, as we saw before, we have 6.7 million Pauli strings. This is like a lot, it's a very, very long linear combination. If you want to measure each of them, even if we group them, this is a huge set of Pauli strings. On top of this, for quantum chemistry, we usually want to have very, very high precision. This is because in order to compute this kind of reaction rates or to learn things about the molecules, we need chemical precision. In this case, it is 10 to the minus 7 precision on each of these operators, meaning that we are going to have to do a lot of circuit executions. In particular, we will need to get these numbers right, 10 to the 14th executions of the circuit in total. If we assume that each execution is 10 microseconds, then we end up with having to run the Q estimation for 30 years. This is assuming that the convergence is going to go well, because, I mean, this type of executions happen at every step of the problem. So we've seen that the quantum chemistry example was not so positive. It's very difficult because of the measurement bottleneck in particular, even though the development of this entity and so on is promising. Let's see another example in which the Hamiltonian is not so complex, so at least we know that the measurement won't be such a problem because we don't have so many Pauli terms. So the example here that I'm focusing on is a paper that it's also quite recent, in which they used a VQE for a Schwinger model. The Schwinger model is a model for high energy physics, so for lattice gate theories. And these are models, like these are lattice models that can follow the device connectivity. So already it's a bit more close to the hardware, and where the Hamiltonian ends up being expressed as a spin Hamiltonian, and it doesn't have so many terms. So we know that the measurement here won't be so difficult. Execution of the ISA circuit in principle won't be so difficult either, because we know that we could in principle find entities that respect the connectivity. So an important thing here would be that if we have a heavy hex topology, we choose a model that follows the heavy hex topology and not, I don't know, some square lattice or some other kind of topology, because this would make it difficult to transpile the circuit. But now let's see, because the problem here would be we don't have very good hints on what should be the parameterized quantum circuit. So before, for quantum chemistry, we said, okay, we don't want to use the hardware efficient just like that, because there's not so many, well, we don't have a physical intuition for that. And on that case, we had the unitary coupled cluster. Here, what's the options if we don't have something like that? Well, the options are many, but one option that was proposed at some point in 2019 that can make a lot of sense, especially if we want to scale to large number of qubits. You see that in this paper they've used 112 qubits, so that's a lot. This would be using adapt VQE. What does adapt VQE do? With adapt VQE, we build the ansatz as we go. So we don't start with a fixed ansatz and then we just change the rotations of the gates. We actually build it as we go. To do that, we need to define some pool of operators that this is kind of the building blocks, and then we're gonna be putting these operators on the ansatz. And usually we define this set of operators by choosing operators that respect the symmetries of our problem. In particular, for lattice gate theories, Hamiltonians have lots of symmetries. And then we know that the ground state will respect the symmetries. So if we start with a state with those symmetries, we want to choose operators that do not break them. And on the other hand, we can define operators that scale well. So we don't want to, for example, put a 2-qubit gate between qubit 0 and 30, because this will imply a lot of different swap gates. So we would choose this type of operators. We initialize our state, and then for each of these operators, we determine the gradient of the cost function with the initial state and the target state. In this way, what we're assessing is, when we implement this operator, how much do we optimize our cost function? And operators that have a big impact on the cost function will stay. Operators that do not impact so much the value of the cost function will go away, because anyway, we're trying to optimize the cost function. So we choose the one with the largest magnitude gradient, we update the ansatz, then we update the parameters, and we keep doing this loop over and over. So here we're kind of optimizing over both the set of parameters and the set of gates. This is good because now we have we're building our parameterized quantum circuit as we go. In cases in which we know very well which should be our parameterized quantum circuit, this is not needed, maybe. But in cases in which it's not clear and we want to reach something that it's not very deep and that it's very optimized over, this is a very good option. And we also keep the number of parameters small, which, as we will see later, it's important for training, because we're reducing the number of gates that kind of we compute gradients on is smaller. We're just taking the important ones. There's more examples recently of other papers that are using that VQE. For example, there was this paper in which VQE was used to create initial states for quantum simulation of scattering in quantum field theories using these W states. This was a paper by John Presky, and it was just released some months ago. So with this, we've seen VQE. We've seen, let's say, a good example in which that VQE was working, and some papers that showed that. Some other examples in quantum chemistry in which VQE was very difficult to implement due to the measurements. And yeah, it has its limitations. We're going to see later which ones they are. And now I'm going to go to the quantum approximate optimization algorithm. So QAOA, it was developed actually in November 2014, not long after VQE. And it can actually be understood as some kind of VQE approach. It's actually a different ansatz for a VQE. What we're trying to do is similar, but since it draws principles from different different quantum algorithms and concepts, and it's used for different type of problems. Let's see it separately from VQE. So QAOA, as I said, it draws principles from different things. One is adiabatic quantum computing, and the other one is trotterized time evolution. So what does adiabatic quantum computing do? The idea of adiabatic quantum computing is to solve optimization problems by initializing a quantum circuit or a quantum system in some ground state of an easy Hamiltonian that we can easily prepare. And then we evolve with a Hamiltonian that depends on time or on some parameter alpha, as you can see here, towards a ground state of another Hamiltonian that it's the cost Hamiltonian that we want to solve. So it turns out that if this evolution is done slow enough, we always stay in the ground state space. And then we end up with a solution of the problem that we were looking for. So you see that here, when we have alpha 0, H is equal to Hs, and this is the easy Hamiltonian. And then as we change alpha, at some point when alpha is equal to 1, H is equal to Hc, which is our cost Hamiltonian. It's what we want to solve. On the other hand, when one wants to implement, if we want to implement this adiabatic quantum computing, we need to implement time evolution with some Hamiltonian in particular here that depends on time. This can be easily done with analog quantum computers, and in some cases they're targeted to do these kind of things. But if we're working with digital quantum computing, we need to implement this as a set of gates. To implement time evolution, we usually use trotterized circuits, so product formulas. What we're doing here is to approximate the big evolution operator, which is the one you can see here in the screen, by a set of time slices, let's say. So each of these evolutions at the delta t can then be approximated as a set of gates. And if we take delta t to be small enough and we take enough slices, our approximation is closer and closer to the actual time evolution. So actually this is you can see here the formula in which you're approximating some state after it's been evolved by this kind of set of operators. Yep, and these are called trotter circuits. So QAOA draws from these two principles. Let's see this for a particular example. And the particular example here is going to be the MaxCat problem. The MaxCat problem is typically used for showing the QAOA. QAOA is useful for combinatorial optimization problems, and this is one of them. In particular, what we want to do here is we take a graph and we want to find the bipartition of the graphs that cuts the largest number of edges. So this can be formalized into some kind of cost function. And this could be the one you can see here in the screen. By minimizing this, you choose the edges to be in the classification of 0 or 1. This puts them in the two bipartitions. And then by minimizing this, we're finding the largest number of cuts. To solve this with QAOA, we need to go a bit further on encoding the problem. And we need to change this into a Kubo formalism. I'm not going to go into detail on how this is done, but this is just changing a bit the problem and expressing as some kind of matrix Q. And this can be easily translated into a Hamiltonian. We want to translate it into a spin Hamiltonian. In this case, we end up with an Ising Hamiltonian. And this is, we have here the couplings between the spins. These are drawn from the Kubo matrix elements. And then we also have this kind of external fields or B parameters that are also drawn from here a bit differently. So it turns out that finding the solution of the MaxCat problem now is encoded as finding the ground state of this Ising Hamiltonian that I'm going to call the cost Hamiltonian. So now we've encoded our problem. We have our cost Hamiltonian defined. How do we implement QAOA? So the answers of QAOA, this is the kind of the implementation, the quantum circuit, is going to be as follows. We want to kind of do something similar as before. Let's start with an easy Hamiltonian. Now I'm going to call this the mixing Hamiltonian. And then move towards the cost Hamiltonian until we converge to the ground state. This is the problem with this, doing it with trotter circuits, is that we would need very, very deep circuits to do this exactly, because we need this evolution to be slow enough so that we don't leave the ground state space. But since we're working with variational quantum algorithms and things here are a bit heuristic, but we want to be adaptable, what we're going to do is we're not going to be doing exactly time evolution. We're just going to put some layers of time evolution, but the delta t, these times, are now going to be our variational parameters. And we let the algorithm and the convergence algorithm decide which are the best time steps that we can take when we mix the two Hamiltonians in order to find the ground state. We're not doing really adiabatic quantum computing. So our initial state now will be the ground state of the mixing Hamiltonian. So usually we take a mixing Hamiltonian that looks like the one in the screen. Its initial state is just the set of, so the superposition of plus states. And then we just need to implement Hadamard's on all the qubits. And then the cos Hamiltonian is the one we described before, and the parameters of our variational ansatz will be these delta t times that now are different for each slice. And these are the gamma 1, B1, gamma 2, B2, and depending on how many layers we want. So this turned out to work quite well in some cases. So yeah, here is the plus state that we start with. And once we do similarly to what I showed before. We have our parameterized ansatz. We build the ISA circuit. Our set of measurements are going to be to find the expectation value of the cos Hamiltonian, which is what we want to minimize. Once we optimize over the problem and we're finished, now a bit of a difference is that here we're interested not so much on the expectation value of the Hamiltonian, because this was helpful to minimize the cost function, but we want to know which is the bipartition. So we need to look at the states. We're going to sample the bit strings from the final state and then take the bit strings with highest probability. And here you see that, for example, the first one that has a high probability, marked in purple, is 10010. So this tells us which of these nodes are in the 1 or in the 0 classification, and it directly tells us which is the bipartition. We can compare the ones with the highest probability and check which one has the largest number of cutting of edges. So QAOA for specific instances can be scaled to solve large graphs, and this is a problem that can be mapped to other problems and can be useful. It's nice because these gamma and beta parameters, they don't increase with the number of qubits. As you've seen, they apply to a whole layer. And if you want to know more in detail how this scaling can be done, you can go to the learning platform. And again, in the course of quantum computing in practice, you would see the details on how to do this scaling. So this has been QAOA as it was first developed. There's been many improvements of QAOA in the literature, as also there's been improvements of VQE and many other variational quantum algorithms. Some examples here. So one could start the QAOA already in a good initialization point so that we converge faster. This could be using some kind of classical pre-processing, and this is called warm start of QAOA. Then also choosing the mixing Hamiltonian has its perks. One can choose a Hamiltonian that kind of makes you stay in some subspace. So the mixing Hamiltonian, at the end, what it does is to get you out a bit of the ground state of the Hamiltonian that you're looking for, so that you don't get stuck in some local minima, for example. But then if it makes you move too much, might also be problematic. So choosing this can also be important. And then there's been many hardware implementations of QAOA. If we want to scale, then one needs to take into account error mitigation, swap strategies, etc. And you can find in the literature how many of these things are done for other problems that maybe are not the max cut problem. In fact, I think it's also interesting to mention that there's been recently a paper going through a different types of problems that can be used for benchmarking this kind of quantum optimization algorithms. And this is also relevant to see which of them can work and in which context. As I said, all of this is very heuristic, but we need ways of studying like when they work and when things need to be improved. So with this, I finished with the QAOA. Now let's go to the QML examples, quantum machine learning. And here I'm going to be very brief, but I thought that QML deserved some mention in this talk because it is a huge field. And there's some very important variational algorithms in the field. So one of them is variational quantum classifiers. Also, they're not so different from what I just presented until now. They're just a bit of steps that need to be added. For variational quantum classifiers, what we want to do is we have a set of data, usually classical data, but it could be quantum data. And we want to classify this data. So we're doing this is a supervised quantum machine learning. So we have a set of training data that has labels, and then we want to use train our algorithm with that set, and then use it for our test data and see if it also classifies it well. So for the training data, we need to encode this data into a quantum state in our QPU. to then apply a parameterized quantum circuit that we're going to train. So to map our data into a quantum state, this can sometimes be a bottleneck. This can be complicated, but there's many options, and these are called feature maps. Also in the Qiskit library, you can find different types of feature maps that can allow you to map the quantum, like the data into a quantum data. A very, for example, straightforward way of doing this, but that then it's not so good because it ends up with having very large circuits, would be encoding the data into amplitudes of quantum states. Then we train our parameterized quantum circuits to optimize our cost function. Our cost function is going to be the difference between the labels that we get and the labels that we want, so that once we've optimized our quantum algorithm, it classifies the data properly. And the rest of the algorithm is similar to what I've explained right now. You can see more details on it in some of the papers. And then we have another type of QML algorithms, which are a bit different and are also interesting and I would say very important in the literature. These are generative models. So here the goal is not classifying data, it's generating new data from some set of data that already exists. So here what we want to do is we want to train an algorithm with a probability distribution of a set of data so that then it's able to generate new data points. Here again, we need to encode the data in our quantum circuit. And in this case, it's not really any feature map that we want here. We really want to encode our data, so the probability distribution of our data as the probability distribution of a quantum state. Then the idea is that we want to train a model that outputs the same probability distribution as the one that we have in our classical data. So for this, we need to train a parameterized quantum circuit so that the output of our data and the model that we have, say that the model that we've defined, are the same. So that this, once it's trained, it's just outputting states in the same fashion as the data that we had at the beginning. And this would be all the different steps of the generative models. Again, most of the details of each of the steps, the optimizers and so on, are similar to what we've discussed in other cases. So with this, I finished with the examples, and now I just wanted to review in more detail some of the things that I've already been mentioning that I think it deserves a whole section on discussing the challenges and open questions of variational quantum algorithms. So there's challenges and open questions in most of the steps of a variational quantum algorithm. For example, for when choosing the ansatz, this is not an easy decision. We need to take into account certain things, the execution on hardware. For the measurement, we've already seen that for quantum chemistry, we have a measurement bottleneck. Now I'm going to try to explain what are some possible solutions to it. Then the cost function evaluation and the parameter optimization. So let's start with the parameter optimization. Let's start from the end. What can be some problems that we can encounter or challenges when trying to optimize over the set of parameters of a quantum circuit? The problems here can be for different reasons, but the most typical ones are barren plateaus and the fact that energy landscapes can be complicated and contain lots of local minima. What are barren plateaus? Well, barren plateaus are the fact that sometimes we get gradients that vanish in most of the area of our Hilbert space. This is because our Hilbert space has a very, very high dimension. The energy landscapes associated to these parameterized quantum circuits are huge, and this provokes the existence of barren plateaus that maybe it's not seen so much in classical algorithms where space of search is not so high in dimension. If the gradients vanish, basically when we're using these gradient-based algorithms, and also the gradient-free algorithms can struggle, we don't really know where to go. Like there's no direction of optimization, so we can basically get lost in the high dimensional space and not find a minimum. And when the energy landscapes are very complicated, it's just easy to get trapped into local minima. Potential solutions of this. Well, barren plateaus, for example, appear because we have very high dimensional energy landscapes. An option that was proposed is, okay, let's take our whole ansatz. It's built with many layers. As we increase the number of layers, we increase also the size of our parameter space. If we start by training one layer and then train the next one and then the next one, maybe we can avoid a bit like finding these areas with gradients that are zero. Another very important way, and maybe the most useful one, of avoiding barren plateaus is starting with a good initialization. We don't always know a good initialization, but in the cases in which we do, we can use some pre-processing, some classical algorithms to find it. Then this would be very, very advisable. And then it was also shown that some models, theoretically, it could be proved that they do not show barren plateaus. These were models with shallow circuits where this is also important, not only the circuit, but the kind of measurements we're doing to reconstruct the cost function. And some of them, well, if you have shallow circuits and local measurements, you don't have barren plateaus. If you have small Lie algebras, if you have certain symmetries, and so on. The problem with this is that it was later shown that most of these models can be classically simulable. So maybe they're not so interesting because we don't really have a reason to use a quantum circuit for this if it's something that an answers that you can create classically. So this is still on the discussion. I believe it's one of the big problems of variational quantum algorithms, but people are researching ways of trying to escape barren plateaus and local minima. Apart from the parameter optimization, then we can also have challenges when executing the ISA circuit. We've already seen this, and there's going to be talks that are going to go into a lot more detail on this, but we have to work with near-term hardware, and this means that we have limitations. We have noise, we have a given connectivity, we have a given size. These are things to be taken into account when deciding things about our algorithms. Potential solutions for this: building adaptable ansatz, for example, the adapt VQE can be helpful, or taking into account the connectivity, as we saw for the hardware efficient or for the local unitary coupled Jastrow ansatz. Then also for the noise, I think there's been a lot of research in trying to see how the noise affects the training of variational quantum algorithm and the solution. So maybe by having noise and then implementing our mitigation techniques, whether the noise changes our energy landscape, there can be situations and maybe even the noise can be helpful with the energy landscape, but this is not clear. So it definitely affects the performance of our algorithms, and it's good to take this into account, and there's a lot of research trying to understand that. And then we can also look at the parameterized quantum circuit. So what are the possible problems here? Well, defining an ansatz, as I said, is a very difficult decision, and there's things that are taken into account, and there's like kind of a trade-off that it's not so clear. You kind of have to find an equilibrium between different things. One thing that I just mentioned before, but I didn't give it a name, is the expressibility. So the expressibility of an ansatz is how many states it can span, it can create. For example, let's imagine an ansatz that is just the identity. This has no expressibility at all, because this is just starting with the state in which we started, which is the 0 state here. If we add a Hadamard and a rotation along the z-axis, then this is a bit more expressible because it can create all the states in the circle that you can see here. If now we add another rotation on the x-axis, then we can create a lot more states on our log sphere. So we see that by adding rotations, by adding parameters, we increase the expressibility of the ansatz, but the problem is that adding rotations means adding more gates. So there's a trade-off between making it more expressible and making it, having it a bit shallow, so that we can run it on noisy devices, and also because of the trainability and the problems with barren plateaus that we were seeing before. There's also another trade-off with ansatz that we've already seen, but just to go through it again, is choosing an ansatz that is problem-motivated or choosing an ansatz that is hardware-motivated. So a problem-motivated ansatz would be the case of the unitary coupled cluster. This is inspired by the physics of the problem. In some cases, we don't know problem-motivated ansatz, and then we have to come up with something different. In some cases, it could be wise to think about the classical algorithms that are used for those systems that we want to study and try to bring some of this knowledge to the quantum design of the ansatz. And this can be done in many ways. And then on the other side, we have the hardware-motivated ansatz. We take into account the connectivity of the hardware, and not only this, but in some cases, we might want to, if we know the noise model of our hardware, what are the best qubits, we know some characteristics that might make it bad for certain things, but might make the device better for others. This is good to take into account. So it's good to take into account the strengths of our device. Combining both approaches is probably the best. And maybe here is a good moment also to mention fractional gates. Fractional gates can implement certain gates on the hardware that when you do that as a circuit, it doesn't grow in like it do not decompose into more gates, so that we can help them keep our depths lower. In cases in which maybe we're choosing something that has a higher depth than what we wanted. And finally, the measurement bottleneck. We've seen that this is a huge problem, especially for quantum chemistry Hamiltonians, in which the number of Pauli strings of our Hamiltonian, of our observable, is huge. Here, there's some potential solutions that this operator grouping that I was mentioning before needs to be done in these cases. It can be done in clever ways. So you have the linear combination of Pauli strings. Some of them have bigger coefficients. Maybe one wants to choose to use more shots for those ones and less shots or circuit executions for other ones. So there's different ways of trying to improve the measurement strategy, but there's going to be a bottleneck on this. It's going to be at some point you're going to hit like when you have so many Pauli terms, you just need to do a lot of executions. Another option for this, and you're going to see a session that dives into this kind of methods, and I think this is very promising, is avoid computing expectation values at all. So in VQAs, in variational quantum algorithms, so far we've seen that we prepare a parameterized quantum ansatz, and then we estimate the expectation value of an observable. And we use this expectation value for the cost function and for the optimization. Now let's imagine that instead we prepare some state with an ansatz with a parameterized quantum circuit, but instead of estimating the expectation value of an observable, we just measure a number of bit strings. This can be, usually needs to be a large number, but still it's just, you can set the number that you want to do there. With this number of bit strings, you could, in principle, classically, in this case, maybe not on a classical computer, but even in an HPC, project your operators there and diagonalize. So take some part of the weight of this, let's say, into the classical computer. Two examples of this that have been quite recent are sample-based quantum diagonalization and sample-based Krylov quantum diagonalization, these sample-based algorithms. And you're going to see a whole session on them. So with this, I want to finish by reviewing a bit this idea that in near-term quantum hardware, we require noise-resilient, shallow, adaptable quantum algorithms. Variational quantum algorithms have many of these characteristics. They're definitely adaptable. They're noise resilient in some cases. We can choose what kind of circuit we want to run. So they have a key ingredient that have been a key ingredient to leverage near-term quantum hardware. They've been very important, and we definitely have seen a lot of different works applied to different use cases using variational quantum algorithms. The problem is that they present challenges in terms of scalability. There's many open challenges still. And then maybe it's good to think about a bit more in a big picture in which, okay, the hybrid idea of using quantum and classical can be very interesting, but maybe parameter optimization is just not the only way of doing it. There's other ways that one can combine quantum and hopefully not only classical computers, but also like HPC, like going to higher architectures for the classical part. So I think this shows promises on the near future in which HPC is used not only for parameter optimization, but also for certain types of post-processing. And then we're going to see how this field develops, and we slowly converge into some algorithms that can show hopefully quantum advantage. With this note, I would like to end. Thank you all for your attention, and we'll be available during the Qiskit Global Summer School to answer any questions. Thank you.